More than 3 decades mark the distance between the abandonment of a wartime aircraft and its eventual recovery. The objective is to securely retrieve a historically significant combat airframe from a remote jungle site. The primary constraint governing this entire investigation is the prolonged environmental isolation of the wreckage. The specific target aircraft is a Mitsubishi A6M2 Model 210. The factory designation is commonly listed as construction number 5784. Reported production records place its manufacture in May 1942, after which the airframe entered the Japanese naval supply system. It is widely associated with the Tainan Kokutai, a naval aviation unit operating from the central hub at Rabaul, and it is treated as a documented artifact from the early Pacific campaign. The end of this aircraft's operational story is best described as abandonment rather than a clearly documented crash sequence. Public records indicate the airframe was damaged and later left behind in the Gasmata area on New Britain, but the precise circumstances and exact date are not uniformly stated across surviving accounts. In 1943, the aircraft was grounded and left completely intact on the perimeter dispersal areas of Gasmata Airfield, located in New Britain. Gasmata functioned as a remote airstrip that was adapted for wartime operations as the fighting shifted across the region. When the operational window closed and forces were ordered to fall back, they faced an immediate, irreversible logistical collapse. Transporting an intact fighter aircraft away from a forward strip requires specialized heavy maritime shipping or dedicated heavy lift equipment. Neither logistical option was available to the retreating units. The airframe simply became stranded. This kind of logistical collapse often forces a specific sequence of decisions on the ground. Abandonment is not always random. It can involve deliberate cannibalization when crews must keep other aircraft flying. A stranded airframe may be reclassified from a combat asset to a source of spares. Ground crews can remove high-value components that are practical to carry, instruments, accessories, weapons fittings, and hardware, while leaving behind a structure that is visibly recognizable but mechanically incomplete. What remains on the dispersal field can be a hollowed shell, shaped more by removal and exposure than by a single dramatic impact event. The transition from an active military airfield to an overgrown refuse dump marks the exact beginning of a 32-year gap in the operational record. Following the final retreat in 1943, the pre-war grass airstrip was rapidly covered by the surrounding environment. The specific geographical location in New Britain was characterized by aggressive, heavy tropical vegetation. The strip fuselage of construction number 5784 was slowly enveloped by the advancing canopy. The former military dispersal area transitioned into a dense, remote aviation archaeology site, entirely isolated from external contact. For 32 years, the airframe lay untouched under humid coastal air, constant rainfall, and dense mud. Because it was abandoned largely intact rather than scattered, parts of the original alignment may still read through the damage, even as corrosion accumulated. Recovery, therefore, depends on a hard physical question: what remains of the aluminum structure and what can still bear handling? Locating the aircraft in the jungle was only the first technical step. The baseline condition of the wreckage dictated whether extraction was even possible. The airframe had survived decades of exposure, yet it remained stranded deep in inaccessible terrain. So the technical task moved beyond find it to understand what is still structurally real. The A6M2's extreme weight discipline, around 3,700 pounds empty depending on configuration, came from thin structure, limited armor, and reduced fuel tank self-sealing compared with many contemporaries, leaving less margin against long-term decay. In conductive coastal mud, dissimilar metals and steel fittings can drive galvanic attack. Moisture becomes the electrolyte, and the thinnest unprotected sections lose integrity first. That mechanism sets the proof ceiling for anything the team hopes to touch, lift, or document. The forensic environment forces discipline. The team cannot trust the aircraft's outline. Panels that look intact can be hollowed by corrosion from within after coatings fail and duralumin sits exposed to rain, humidity, and mud. With little heavy armor to absorb localized damage, even the main load paths can be compromised where the structure is thinnest. Assessing this decay requires mapping exactly which sections of the airframe have dissolved and which retain enough mass to hold their own weight. The mud traps moisture directly against the lower fuselage and the critical wing center sections. The wing spar carry-through structure, which serves as the central anchor point for the entire aircraft, absorbs the highest concentration of galvanic decay. Fungi and dense biological growth penetrate the overlapping skin panels, compromising the riveted seams from the inside out. The integrity of the original factory joints becomes entirely compromised by the continuous electrochemical reactions. Forensic assessment targets the junctions that fail first, factory joins where different alloys meet, and where steel bolts, brackets, or fittings sit against aluminum. In mud, when those dissimilar contacts become localized catalysts, corrosion accelerates at the joint, rigidity begins to collapse, and thin bulkheads and stringers, already built to minimal tolerances, can drop below their load threshold after only fractional material loss. This continuous degradation strictly bounds any future handling or physical interaction with the airframe. The severe biological intrusion accelerates the breakdown of any remaining organic materials, such as fabric control surfaces and internal seat components, leaving only the compromised metallic skeleton. The forensic problem is not simply identifying the remaining parts, but determining if those parts can withstand the physical handling required for a comprehensive survey. If the primary wing spars are critically degraded, moving the aircraft requires an entirely different set of operational trade-offs. Over time, the jungle does not just hide the evidence, it reshapes it. Surface continuity can be misleading, so the investigation shifts from silhouette to measurable condition, mapping decay gradients, testing what still holds load, and prioritizing the few surviving details that can be documented without destroying them. The question becomes narrower and harder. Can a heavily degraded shell still carry proof strong enough to name a specific combat pilot? Operational records and later secondary accounts from the early summer of 1942 have not always agreed on the exact tailcode linked to Saburo Sakai's primary mount. Some narratives have long associated him with V-172 during that period. Meanwhile, other attributions, including the markings presented on the recovered airframe, point to V-173. The dispute is less about whether he flew with the Tainan Kokutai than about which specific coded airframe best matches the surviving evidence. Relying solely on paper records introduces significant risk into any historical investigation. Administrative documents represent operational intent at a specific moment in time. They frequently fail to capture field-level aircraft swaps, rapid maintenance rotations, or localized repainting driven by combat damage. The high operational tempo of the Tainan Kokutai meant that pilots often flew whichever airframe was mechanically ready on the flight line. In forensic aviation archaeology, physical evidence directly extracted from the site always supersedes administrative paperwork. The verification of identity in this specific case relies entirely on the precise recovery of original paint stencils. Investigators carefully examining the structural sections from the site located an intact sequence marking preserved on the tail structure. The recovered stencil clearly displayed a distinct fourth-line extension specifying the tail code V-173. This isolated physical artifact provided a definitive, unyielding contradiction to the accepted historical narrative surrounding the pilot. Resolving this discrepancy requires applying the logbook versus stencil verification method. Forensic identity proof demands multiple, overlapping points of corroboration to eliminate any margin of uncertainty. The painted stencil alone only confirms a unit operational code applied in the field. To achieve absolute verification, this field code must be permanently tied to the specific factory manufacturing data. Investigators map the newly discovered tail code V-173 directly to the factory construction number 5784. By cross-referencing production data with surviving markings and restoration documentation, the investigative team strengthened the attribution of this airframe to Saburo Sakai. The combined evidence can outweigh earlier assumptions drawn from incomplete or generalized unit paperwork, but responsible curatorial language still treats parts of the wartime record with caution. The result is a widely accepted identification anchored in physical remnants and institutional documentation, rather than a claim of perfect certainty. Establishing this direct physical link completely alters the operational priority of the recovery effort. The airframe ceases to be categorized as a generic A6M2 target. It is immediately reclassified as a highly specific, historically verified artifact of immense institutional value. The confirmed provenance shifts the operation from a standard wreckage documentation survey into a targeted historical extraction. The imperative to retrieve the structure increases exponentially once the precise identity is locked and verified through the primary anchor proof. With the aircraft's identity locked, the team's objective pivots, the forensic phase ends, and extraction begins. The team now holds an authenticated artifact, but terrain makes heavy vehicle access impossible, and the remaining structure is too fragile to treat like ordinary wreckage. The constraint has shifted from identity to geometry. How do you move large, rigid sections out of dense jungle with no heavy lift available? Sacrificing intact structural integrity to guarantee historical preservation creates the ultimate operational trade-off. The physical dimensions of the targeted aircraft present a rigid, unyielding geometric problem for the recovery team. While the verified identity of the airframe demands retrieval, the remote terrain can block standard heavy lift options. In that context, recovery may depend on whatever light tactical transport support is actually available in theater, including aircraft in the DHC-4 Caribou class that operated across Papua New Guinea in the period, rather than on an ideal, purpose-built heavy lift plan. The engineering specifications of this specific transport dictate an absolute limit on the size of any recovered artifact. The tactical aircraft features a rear cargo ramp designed for tightly defined payload dimensions. The primary fuselage of the recovered fighter, combined with its fully integrated central wing root structure, significantly exceeds the maximum allowable width of the cargo hold. A rigid aluminum airframe cannot be compressed, folded, or manipulated into a space smaller than its fixed geometry. The recovery team confronts a stark binary decision. They must either abandon the authenticated wreckage entirely, or they must deliberately destroy its physical continuity in the field. Because the factory assembly depended on thousands of permanent flush rivets and tightly integrated load paths, and the airframe could not be broken down into clean, bolt-off modules in the field. To meet strict transport dimensions, the team reportedly sectioned the structure into smaller pieces, an invasive choice that permanently altered factory joints. With no heavy field cranes, ground crews then manhandled the severed wings, tail section, and central fuselage block up the transport's rear ramp, and secured them inside the confined hold, balancing the load for flight. With the sectioned wreckage secured, the recovered components were moved out of the forward area to a rear logistics site, commonly reported as Port Moresby, where they could be held and organized for onward transport. After a period of storage and handling, the airframe was ultimately shipped to Australia, entering the next phase of reconstruction and curation. The primary extraction objective is successfully achieved, but the operational cost remains exceptionally high. A recognized historical asset was intentionally cut into pieces with power equipment to overcome a logistical limit, an extreme step that signals a closing boundary, not a preferred method. The choice suggests that whatever pressure surrounded the operation was external and time-driven, forcing the team to accept permanent damage in exchange for extraction. The 16th of September 1975 created a hard boundary. Papua New Guinea's independence tightened the legal and administrative climate around cultural property and export consent. The team was not racing weather or sudden collapse. It was racing a closing permissions regime that could become far more restrictive after sovereignty. In practical terms, the removal after the transition risked prohibition, turning the mission into a calendar-driven binary: extract while authorization still exists or leave the verified airframe behind. This hard legal boundary fundamentally alters the standard procedures of aviation archaeology. A conventional recovery operation relies on patience, careful logistical planning, and waiting for the optimal heavy transport to ensure maximum structural preservation. The team would normally stabilize the site, construct proper access routes, coordinate with heavy shipping, and wait for maritime lift capability to become available. The Independence deadline completely eliminates the option of waiting. The team cannot delay the operation to secure ideal conditions because their legal authorization to execute the salvage will permanently expire in a matter of months. The rapidly closing legal window forces an extreme operational trade-off. The team must accept the immediate availability of limited transport assets entirely regardless of the physical impact on the artifact itself. The decision to execute a rapid, aggressive removal is strictly dictated by the geopolitical timeline. If the recovery crew leaves the remote dispersal field to requisition better equipment or heavier lift capability, the sovereign boundary will close before they can return. The airframe would be permanently trapped behind an impenetrable legal barrier, left to continue degrading in the tropical mud with zero chance of future retrieval. Faced with the deadline, the team commits to immediate extraction for one procedural reason: preserving custody. Moving a compromised artifact out of the tightening jurisdiction is judged preferable to leaving better structure permanently trapped behind a post-transition prohibition. So the operation focuses on crossing the geopolitical threshold while the authorization window still holds. The rapid execution successfully pulls the historical structure across the boundary just before the sovereign window closes permanently. The military team effectively secures the asset and safely relocates it out of the newly restricted territory. The operation successfully bypasses the legal lockdown, but the consequence of the forced timeline immediately creates the next major constraint. The tactical victory results in a heavily fragmented, severely degraded structure sitting in a rear logistical depot. The historical identity is preserved, and the legal extraction is complete, but the physical condition of the hardware is extremely poor. Rebuilding a specialized aluminum structure demands massive financial resources and thousands of hours of highly skilled sheet metal work. Who repairs a severely corroded field-cut airframe when standard military budgets strictly forbid a specialized professional restoration contract? A fragmented, corroded airframe quickly became a liability at the rear depot. It needed funding and skilled labor that ordinary military budgets could not sustain for a bespoke restoration. Rather than leave the parts in indefinite storage, the holding authority routed the structure to the School of Technical Training at the Wagga base, turning reconstruction into an apprentice program under instructional oversight. This institutional decision dictated a completely different pace and methodology for the reconstruction. The restoration would not be a rapid, commercially driven salvage effort designed to quickly place an aircraft into a museum. Instead, the fragmented structure became a rigid procedural exercise for inexperienced personnel working under strict instructional oversight. The severely compromised state of the aluminum structure provided a comprehensive baseline for teaching advanced aviation sheet metal fabrication. Instructors utilized the precise physical trauma inflicted upon the structure during earlier phases as the primary technical challenge for the trainees. Reassembling a severed airframe demands far more precision than assembling new factory parts, forcing the apprentices to constantly solve complex alignment geometries. Over a continuous 5-year period, successive classes of apprentices systematically addressed the severe structural deficits. The primary technical hurdle involved reversing the deliberate severing of the main load-bearing paths. The students had to meticulously map the divided fuselage bulkheads and the sheared wing spars. Because the structural continuity had been completely broken, the apprentices could not simply rivet new external skin panels over the empty gaps. To restore the required rigidity, they had to engineer and fabricate precise internal splicing plates. These custom fabricated plates had to match the exact metallurgical tolerances and geometric curves of the original manufacturing standards, ensuring that the heavy static loads of the finished aircraft would transfer correctly across the spliced joints. The extended timeline allowed for an extremely methodical approach to stabilizing the remaining galvanic decay. Trainees systematically drilled out thousands of compromised flush rivets to completely remove the heavily corroded internal stringers. The instructional process strictly forbade patching over active corrosion. Each degraded aluminum component was carefully extracted, measured, and utilized strictly as a physical template. The apprentices then fabricated exact dimensional replicas from viable modern aviation-grade materials using manual shear and brake-forming tools. Temporary fasteners were utilized to hold the complex curved panels in perfect tension before the final solid rivets were driven into place. This supervised reverse engineering process ensured that the final structure maintained strict adherence to the original aerodynamic profile, while simultaneously neutralizing the persistent chemical hazards previously embedded in the original metal. The methodical reconstruction converted the fragmented pieces back into a structurally continuous airframe, stabilizing the artifact for long-term display. Once the instructional program concluded, the completed aircraft was prepared for institutional transfer, and the military formally relinquished it to civilian curatorial control. By 1986, the restored fighter had returned to the Australian War Memorial for completion and long-term care, ultimately entering static display as a centerpiece artifact. A final, human coda to this extended technical process is linked to the original pilot himself. Saburo Sakai is reported to have visited Australia and viewed a zero display associated with him, adding an emotional weight that no document can replicate. But the historical attribution ultimately rests on curatorial records, restoration documentation, and the surviving physical evidence, not on a single moment of personal recognition. The chain of custody, from a remote dispersal field to institutional care, preserved a rare physical record of an early Pacific air campaign.